7 is the only prime. Within a certain domain, the domain that we're using matters. It changes our perspective. In the integers, there are infinite primes. It's not just 7. But if we change our perspective to the real numbers, there are no primes. In the integers, 7 limits factorization. We can only factor it in a boring way. But that doesn't happen in the real numbers. 7 is 3 times 7 thirds, or e times 7 eighths, or any x times 7x, 7 over x. Division is very easy in the reals, so the whole idea of primes is pointless. And the same reasoning applies to the rationals. There are no rational primes. But there are some weird domains between the integers and the rationals that have just one prime, or two primes, or any finite number of primes. In this video, we'll see how to construct these domains, and along the way, we'll learn to think about primes like a mathematician. So, how do we make 7 the only prime? When going from the integers to the rationals, we lost all the primes because they got divided out. So we can keep 7 if we don't divide it. We'll take our domain, let's call it D7, to be all rational numbers where the denominator is not divisible by 7. This means that any other prime, such as 5, can appear in the denominator, so it gets cancelled out, but 7 can't. 7 is left as the only meaningful prime. And intuitively this makes sense, but we need to talk about some of the details. This domain allows 7 to factor a lot of different ways. 7 is 2 times 7 halves, or 3 times 7 thirds, and so on. There are infinite ways to factorize 7 in D7, yet it's still prime. In the integers, 7 only has one factorization. But that's not what makes it prime. It's not even true. If we're using all the integers, then there are 2 factorizations. The whole point of primes is that they give us unique factorization. If we factor a number, we always end up with the same primes. This is what we care about. So what makes this happen? Let's look at this factorization. We'll replace each number with its prime factors. And we notice that at each step, we send some primes to the left and some primes to the right. It's always a one-to-one map. If the number includes a 7, then one of its factors will include a 7. This is the property that we're looking for. It allows unique factorization since factoring doesn't change the total set of primes. So a number p is prime if, when p divides a, and a is factored into b and c, then p divides b or c. Factoring carries forward divisibility. And this isn't true of composites. 4 divides 12, but it divides neither 2 nor 6. So this is a good test of being prime. Now let's apply this to D7 to show that 7 is prime. Let's say 7 divides some number, 7 times the numerator and denominator. If that number is factored into 2 new numerators and denominators, then if 7 is prime, it must divide one of the factors. To show that it does, let's multiply both sides by all 3 denominators and cancel, and we now have just integers. 7 divides the left, so it must divide the right. But 7 cannot divide the denominator because we're in D7, so it must divide one of those numerators, meaning that it divides that factor too. And that's what we wanted to show. Factoring carries forward divisibility. So 7 is prime in D7. It acts a little different from the integer primes that we're used to, but it's still prime. So now we should ask, is it the only prime? That's the reason that we made D7. But using just this factoring definition, it's not. 2 is also prime. If 2 divides some a, then it will divide b and c because 2 divides everything, since we can put 2 in the denominator. So 2 follows the factorization rule, but that doesn't really mean much because 2 just divides everything anyway. This is like saying that 1 is a prime in the integers. It technically follows the rule, but only because it divides everything. So in this case, we make an exception. 1 is called a unit. Primes are the numbers that follow the factorization rule and aren't units. They're the ones that follow the factorization rule in an interesting way. And then composites are everything else. Let's see how this applies to the real numbers. Well, everything is a unit. Everything divides everything else. Any x divides y, since y equals x times y xths. There are no primes because there's too much divisibility. And we notice this happens because every x can be flipped into 1 over x. So the units are just the numbers that can be flipped. Okay, so how does this apply to D7? What are the units? What can be flipped? Remember, the denominator cannot be divisible by 7. So in order to flip, the numerator also can't be divisible by 7. But that's all that we need. This is the form for a unit. And notice that this includes all integer primes except for 7. They have all become units. So what's left over? The multiples of 7. And we can factor out any 7s to get a unit times a power of 7. This is the general form for a number in D7. When the power is 0, the number is a unit. When the power is 1, the number is a prime. And when the power is greater than 1, the number is composite. So a number's prime factorization is just determined by its power of 7. 7 is the only prime. Right? It doesn't seem like it. There are still infinite primes. Any unit times 7 is a prime, so 7 halves is a prime, 21 fifths is a prime, and so on. But there is a sense in which these are all the same prime. We just need to think about primes differently. Let's go back to the familiar primes. We usually think of them in the natural numbers. If we try to extend to all integers, we get these negative primes. And this breaks unique factorization. Now there's a bunch of different ways to factor 420. But they're not that different. We just have positive and negative versions of each prime. So 7 and negative 7 kind of act like the same prime. Ideally, we would have a way to consider them equal. And there is a way. Instead of primes being numbers, we can think of them as sets of numbers. These sets are called ideals. So the 7 ideal is all the multiples of 7, and the negative 7 ideal is all the multiples of negative 7, and notice, these ideals are the same. So in this way, they're the same prime. And just like numbers, we can combine ideals. The 2 ideal times the 7 ideal is all multiples of 2 times all multiples of 7, which ends up being all the multiples of 14, the 14 ideal. So multiplication makes sense, and this gives us unique factorization. The 420 ideal is the product of all of these prime ideals, and this is unique. So now let's apply this back to D7. We have just one prime ideal, the 7 ideal. The ideal from any other prime, a unit times 7, is equal to the 7 ideal. So there we are. D7 is a domain where 7 is the only prime. We created D7 by taking the integers and dividing by the complement of the 7 ideal, everything that's outside of the 7 ideal. This process is called localization. We could also do this with the 2 ideal to make 2 the only prime, or with the 3 ideal, or any other prime ideal. Localization gives us a local ring, a structure with only one maximal prime ideal. Now notice this key word, maximal. There's not necessarily one prime ideal, just one that's maximal. In D7, there was only one prime, but in other cases we could get a maximal prime ideal that contains some other primes. This happens because ideals are weird. The multiples of n is a very common type of ideal, but there are other kinds. An ideal just has to follow 2 rules: closed addition and vacuum multiplication. So, for example, with the 7 ideal, adding 2 multiples of 7 gives another multiple of 7. Addition is closed. And multiplying a multiple of 7 with anything gives a multiple of 7. Multiplication acts as a vacuum. The ideal pulls everything into it. So now let's look at an ideal that's not just multiples. We'll take our domain to be the integer polynomials, and the ideal E is the set of polynomials with an even constant. This has closed addition and vacuum multiplication, so it's an ideal. And E is prime, since factoring an element from E always gives another element from E. And weirdly, it contains other primes. E contains all the multiples of 2 and all the multiples of x. So if we localize by E, we get E as the only maximal prime, but the 2 and x ideals are smaller primes. Polynomial primes are really interesting, and I'll be talking more about them in my next video. To wrap up this one, let's go back to the integers. We can broaden this localization idea to get multiple maximal primes. So if we divide by everything that's not divisible by 2 or 3, we end up with a domain where 2 and 3 are the only primes. And we can add in 5 and 7. This idea generalizes to any n primes. Given any set of primes, we can construct a domain where they're the only primes. And I think that's pretty cool. Thanks for watching, and I'll see you soon for some more fun with primes.